Ok, it's now recording. Good morning, everybody. Bom dia a todos. Espero que todos estejam bem aí. Let's continue what we have seen last two classes. First of all, I'd like to ask you if you have any questions, any doubt about what we talked about in last two classes. If you have any questions, let me know. Okay. So if you don't, I will start doing a review, because today we are gonna finish the part of numerical part of the simulations. Okay, so I'll do a brief review here. If you have any questions, just stop me. Okay. So what we have seen so far is that we are working mainly with mass balance equations. Sorry, this is in Portuguese. I picked the wrong one. So okay, it's just a review. I'll put just the equations here. I pick up the Portuguese version, but what we are seeing is just that we are going from the physical model to the mathematical model. So the physical model have to describe all the information we have, that is the loss that we have to include to model in the reservoir. Then we transform this into equations in the mathematical model. Once we have these equations that are hard to solve because of the boundary conditions and the complexity of the reservoir, we try to solve it numerically, as we are seeing in these two classes, and then we transform this in the computer program, that is the reservoir simulation that you are using. We have talked that we have mainly three models. Of course, we have a lot of different models, but these are the main important models that we have in the companies. The first one is the black oil. The second one is the compositional, and the thermal. We are not seeing these two models in this class because it's just an introductory class. But once we explain the equations of the black oil that we are seeing in these two classes and today, it's not difficult for you to go from the black oil to the other models. Okay. The basic difference is that in the compositional model, we have to include the time dynamics of the phase behavior. In the black oil model, this is very simplified, as we have seen in the classes. We just transform this into a table. And in the thermal model, we have to include the temperature change and the consequence it have in the phase behavior. Okay, so if you need to use in our future work one of these two models, you have to study a little bit more than we have seen, but the equations are basically the same, including the time dynamics of the phase behavior to model how the fluid will behave in the process. Okay. So the first part is the physical model. As we have seen, we have to integrate all the properties we have: seismic data, maps, logs, and laboratory experiments, and so on. And we have to model all the complexity of the reservoir that we have. We have to put everything together in the simulator, and we have seen. And the basic problem that we have, one of the basic problems we have in the reservoir simulation area, is that we are trying to model a physical thing that's happening in the porous media, and our blocks are very large compared to what we are modeling. Sometimes we have more blocks, for example, of 100 meters by 2, 3, 5, even 10 meters in the vertical direction. So once we go from here to here, we have a lot of errors, numerical errors, that we have to be aware of when we are using simulation. Okay, and this is what we are trying to see in these classes. Okay, so this is a summary of the beginning. So we have the conservation laws that we are using basically in this class, mass conservation laws. The physical behavior we have to include is capillary pressure and the phase behavior of the fluids. For the black oil model, we have seen that this phase behavior is very simple. It's just a table where we plot all the properties as a function of pressure. Okay. We have also some additional equations that we are including in our thing. That's we know that all the saturations have to add 1 at the end, and all the molar fractions have to add 1 at the end. This is for the composition, okay? Once we have all this into simulators, we have initial conditions. We are gonna see today how are the initial conditions for the reservoir. The boundary conditions we are also gonna see today. The wells also we're gonna see in the class today. And also we have to treat the aquifers that we can treat it differently, as we have seen in last classes. I can put the aquifer inside the grid, or I can treat the aquifer as an analytical boundary condition for the reservoir, okay? So in the reservoir simulation manuals, we have a lot of information how we treat these aquifers in this way. We're not going to see too much of this in the class today. So once we have this physical model, we go into the mass balance equations. As we have seen, we have seen how we do the mass balance equations in one block of the simulator, and how we solve all these equations together, all the blocks together at the same time. And in order to do that, we are going to use the Darcy's law, which you have seen in reservoir engineering classes. If you are not taking reservoir engineering classes, then you are not familiar with that. It's very important for you to understand the Darcy's law, okay? For those who are not engineers and are not familiar, it's important to understand, because this is the basic law we're going to use to model how the fluid will move from block to block, okay? And we have also the capillary pressure relationship, the phase equilibrium phase, that we are going to treat the fluids. The saturations and the molar fractions add to 1, as we have seen. So these equations will be the basic equations we're going to use in the reservoir simulation. And as we have seen in last class, what we're going to do is take block by block, compute the mass that's going into the block, the mass that's going out of the block, and the mass that's accumulating in the block. The mass that's going in and out can be from block to block, and from block to well, or from well to block, okay? So we have to compute all this mass. And if you have, we have seen all the equations. If you have questions, just stop me. But we have, at the end, this is the Darcy's law that we have to include. So for us, in the reservoir simulation, black oil models and compositional model, the fluid is moving because of difference in pressure. So if I have two blocks, block 1 and block 2, for example, the fluid is going to move from one block to another because of the difference in the pressure, or the difference in the gravity, okay? So the fluid will move because of the gravity, which is this part here, or the fluid will move because of the difference in pressure. For example, if the pressure in block 1 is higher than the pressure in block 2, the fluid is going to move from block 1 to block 2, and so on. So if I have a reservoir and I have an injector here, for example, initially I have the reservoir is in equilibrium, but once I inject fluid into this block, I'm going to increase the pressure of this block, so the fluid is going to move from this block to the neighbors. And the same thing happens to the producer. For example, if I'm going to take fluid from this block, I'm going to decrease the pressure here, so the neighbors will have a pressure that is higher than this one, so the fluid is going to move to the producer. So this is the basic physical meaning of this, the Darcy's law, okay? I didn't include here, but we have also the capillary pressure that sometimes can be important for us, so they are inside the equations as well. So this difference in pressure here, as you can see, is the pressure of the phase. So if I have a different pressures from the water phase and the oil phase, also this is also part of the physical explanation for why the fluid is moving from one block to another, okay? So it's moving because of difference in pressure. It can be pressure, absolute pressure, or capillary pressure. and also gravity, okay? So once we include all this in the equations, and we have seen how we are going to, this is an important thing that we're going to use a lot in the simulation. It's called transmissibility. So the transmissibility accounts for all the properties that are important when the fluid is moving from one block to another. So the area is important because, of course, if the area is higher, is bigger here, I'm going to move more fluid. The fluid property is also important. This is the density and the viscosity. They will report also if the fluid is moving from this block to this block. These are the important fluid properties that is going to influence the transmissibility from one block to another. Of course, the amount of the component that's in this thing. The permeability is also important. If the permeability is higher, I'm going to have a higher velocity here. And the relative permeability as well is important because, as we're going to see in Darcy's law, this is the permeability of the phase, okay? And also the distance between the two blocks will be important for the transmissibility. So once I have all these properties here, I can calculate how much is the transmissibility of each pair of blocks, okay? So the transmissibility is a property of the interface between the blocks. And how, if the transmissibility is higher, the fluid has a higher chance to move in a higher velocity, okay? So at the end, we are going to end up with this. I didn't see, but we have the number of equations that is equal to the number of unknowns in our problem, okay? So we are going to solve the equations, and these are the equations for the black oil model, okay, that we have seen in last class. Again, every time, all the simulators that are governed by these laws, we have these equations. This part here that we call this part here is the accumulation term, which is the amount of fluid that is accumulating in the block. This term here is the well term, which is the amount of fluid that's going in or out the block because of the well. And this is the term, that is the transmissibility term, that's from block to block. The fluid is going to move from one block to another according to this term here. So we have three terms here. This is the movement from block to block, the movement from block to well, and the accumulation. So if you add these three terms here, we have the amount of the conservation of mass in the block. In the black oil, as we have, I didn't have here, but as we have the oil component only in the water phase, I have just one term here. The heavy component, which we call oil, is only in the heavier phase, in the oil phase, so we have just one term here. And the gas term, which is the lighter components of the hydrocarbons, can be in the gas phase, or they can be inside the oil phase, okay? So for example, C1 and C2, which are lighter components of the hydrocarbons, then can, depending on the pressure, they can be in the gas phase, or they can be inside the oil phase. So when we account for the gas conservation equation, we have to take into account these two terms, okay? In the transmissibility term here, and also in the accumulation term, because we can have free gas in the block, or we can have gas inside the oil phase. And also for the well, we can have free gas being produced from the reservoir, or we can have gas that's being produced inside the oil phase, okay? So this is the more complex, and this is the basic black oil equations. There are some a little bit more complex black oil equations where we have also the heavy component in the lighter phase, in the gas phase, but this is not the case here. We're gonna study here just the basic equations for the black oil, which is the equations that are in most of the black oil commercial simulators. It's exactly this one, okay? So this is the most important equations you have to understand in these two classes, because this is, it's very important. we are going to solve these equations for all the blocks in the reservoir. Okay, so if you have, for example, 1 million blocks in your reservoir simulation, we're going to have 3 million equations to solve, because we have to account for the water mass balance equations, the oil balance equations, and the gas balance equations. Okay. Any questions? Okay. If you don't have any questions, just we're gonna follow. So here I'm trying to show how we are gonna solve these equations. So again, for the equations, we have the accumulation term, which is this one. Sorry, this is in Portuguese, but it's just a review. This is the flux term, or the transmissibility term that we call, which is the mass from block to the neighbors here. So here I'm trying to show the block and the neighbors. In this case, is 1, 2, 3, and 4. And the amount of the components that is gonna move from block to another is proportional to the potential. And remember, this potential is difference in pressure, difference in height because of the gravity, and difference in capillary pressure. So we have, if you have a different potential in the phase, we're gonna multiply this by the transmissibility, and then we're gonna have the amount of fluid that's going from this block to the neighbors, okay? And again, the transmissibility accounts for a geometric term, which is because it's proportional to the size of the grid and permeability and so on. It's important because of the fluids. Here we're gonna see that the relative permeability and the viscosity basically are the mobility of the phase here. Okay, if you are taking reservoir engineering classes, you know very well what is mobility. But mobility is how easy the fluid can move from one block to another. For example, the mobility of gas is higher from compared to the mobility of oil, because the viscosity of the gas is much lighter than is much smaller than the viscosity of oil, for example, and so on. If the relative permeability is higher, we're going to have a higher transmissibility, and so on. And this term here, of course, it accounts for the solubility of the component in the phase. Okay, so we are not going too deep into the explanation of this, because this is more a subject of the reservoir engineering classes. Here is just to explain how the simulator works. Okay, so once we have simulators, here I'm giving examples how we calculate these geometric factors from block to block for coordinates and for cylindrical blocks. And of course, if I have more complex grid, we have more complex geometric factor, but that's the only thing that changes when we change the grid, okay? Because of this term depends on the geometry of the grid, depends on the area between the blocks and the distance and the permeability, okay? And here, just examples. Each grid has similar examples as this one. We have to calculate a geometric factor, which gives that have to account for how easy is the transmissibility from block to another. Okay. The well term it's easy. You just have to account for the amount of components that's going in and out. And if you have taking this amount of gas that's going in and out, we have to know how much of the phase is going in and out of the block. For example, if we are injecting water in the block, the water is only in the water phase, so we account for the water that's being injected. If you have a producer well, we're gonna study today how is the well behavior, but we have to account for the phases that are in the block and the phases that are being produced from the block. So if you have a producing of the phase oil, for example, then I have to account for the components that are inside the phase oil, and then I'm going to produce gas and oil and so forth, so on and so forth. Okay. Okay. So these are the most important equations that you have to understand, and these are the important thing how we are going to solve these equations. So the most important thing is that we have 3 equations per block, so we're going to have 3 unknowns. The most typical unknowns we have in the reservoir simulations can be others, but is the oil pressure, water saturation, and gas saturation. Okay. Once we solve for these 3 variables, the water pressure, for example, we can take because we know the capillary pressure from water oil. So if we know the oil pressure, we can calculate the water pressure. The gas pressure, for example, we calculate from the capillary pressure from oil gas here. So if you know the capillary pressure and we know the oil pressure, we can calculate the gas pressure. So we don't have to solve for these 2 variables, because once we know one, we can calculate the others, okay? And the same thing for oil saturation. For example, we know that oil saturation plus gas saturation plus water saturation is 1, okay? So once we calculate for water and gas, then we can calculate the oil. So we don't have to solve all the equations for 6 variables. We just solve the equations for 3 variables, and the others we can calculate from these 3, okay? So from this point on, we are going to treat all the equations as we have these 3 unknowns, okay? And again, if you have questions, let me know. So how we are going to solve these equations? So this is the basic equations we have seen. So these are these 3 equations here, okay? But these are written in the more general term. It can be oil, can be water, or can be gas. So we know that the amount of fluid that's going into the block through the boundaries and through the well is the amount of fluid that's accumulating in the block. So we know that this is 0, okay? So how we are going to solve the equations? We are going to call this the residuals. So for each equation, we have the residue of the component in that block, okay? And as it's very difficult to solve this analytically, we're going to solve this numerically. So we are going to guess, give an initial guess of pressure saturations. Once we have an initial guess of this, we're going to put in this equation and check if this equation is 0. If it is not 0, that means that this is not the solution of our equation. So we are going to calculate the derivatives and then give another guess and so on. So this is called the Newton-Hamson iterative procedure. For those who are engineers, probably you have used this several times to solve this type of equations. But the basic idea is, I'm giving here in just one equation. For example, if you have a residue, this is the initial guess. I'm going to give the initial guess. For example, if I have a very simple equations to solve, for example, the residue is, for example, ax squared plus b, for example. And then I have to solve for this. I know that this must be 0. So instead of solving this equation, I can give a guess for x. Then I'm going to calculate the residual here. So the residual is not 0. So if the residual is not here, I'm going to calculate this derivative here. This derivative will give the second value of x. Then I'm going to calculate the residual again, then the derivative, and so on, until I reach this point that's close to 0. So instead of solving this analytically, I'm going to solve this numerically using this equation. So this is the x, in this case, is the variable. R is the residual. And the derivative here is called Jacobian Matrix. Probably, if you have seen Reservoir Simulation Class before, you have heard about this term, which is the Jacobian Matrix. It's very simple. It's just a matrix of the derivatives of the terms, which I'm going to calculate to try to find the next value of x in this case, okay? So this is an example how I solve this using this Newton-Hamson process. Of course, this method will converge if I'm very close to the solution. So sometimes you have convergence problems in the simulations. I don't know if this is happening in your projects. This convergence problems is very common to happen in very complex reservoir simulations, like compositional models and so on. Once I have a lot of variables and complex solutions. And we have ways, I'm going to talk a little bit of some ways to solve this convergence, but once this Newton-Hamson is just work if I have a gas that's very close to the solution. If I have a time step, for example, of 30 days, and I'm trying to find the solution for the next 30 days, and I try to converge these equations in 10 iterations, and I didn't reach convergence, for example, that it's meaning that the solution is not converging. So what the simulation does do, it goes back to the original point, then it cuts the time step in 15, in half, for example, in this case, 15 days. Why it does like this? Because the solutions is very hard to solve for 30 days, but then the simulation tries to solve for 15 days. And 15 days, the solution is closer to the day 0 here. So it's going to be a little bit easier to find the solution. If, again, I don't reach convergence, it cuts the time step in half and tries to converge this again. For example, let's assume that, okay, I could find the solution here. So then I go to the next time step and so on and so on. So this is one of the causes that, I don't know if it's happening in your projects, but for complex grids and complex solutions, this happens many times in the simulation. It tries to solve for a time step. If I don't reach solution, then I go back to half of the time step and then try again until we reach convergence. Once I have convergence, it starts out the process again and so on. Okay? So this is the basic concept, very superficially, but if you have any questions or if you have any comments to do, let me know. But this is the type of equation that's solved. So instead of solving just for one equation and one variable, the simulation will solve for many equations, many variables. Again, if I have 3 equations per block, so if I have 1,000 blocks, I have 3,000 equations to solve, okay? And for this grid here, we are showing the solution. For example, a very simple grid here, where I have these 12 blocks. I have these 12 points here. Remember that each X here is a matrix 3 by 3, okay? So in this matrix here, 3 by 3, I'm solving for pressure. I'm solving for pressure, for water saturation and gas saturation of block 1, okay? And here is the equation of oil, equation of water, and equation of gas, okay? So because all the variables of block 1 are important for the mass balance equation of the phases in block 1, I have terms here. Because the block 2 is a neighbor of block 1, as we have seen here, then the variables of block 2 are also important when I'm solving the equations for block 1. Also, because block 1 is a neighbor of block 5, I have terms here because the pressure of block 5 and the saturation of block 5 have to be included when I'm doing the equations of block 1. So when I solve for block 1, I have variables of block 1, block 2, and block 5. When I'm solving for block 2, I have equations for block 1, block 3, and block 6, as here, 1, 3, and 6, okay? And then I do for all the blocks like this way. And that's why I have to solve all the equations at the same time, because when I'm solving for block 1, the variables of block 2 are also important. When I'm solving for block 6, variables of block 10, 5, 2, and 7 are important. So I have to solve all the equations at the same time. That's why I use this Newton-Hamson method trying to solve, because there are many equations and many variables, and that's why I solve these equations in this way, okay? So for each x here, for each term, there is a question here. Do the simulation solve all the equation in each time step? I mean, when do we divide time step by two? Yes, what I'm saying that, for example, I have here time 0. And then what I'm saying when I'm solving this term here, in terms here, it means that I know pressure in time 0 here. I know the water saturation in time 0 that we call N here, and we know the gas saturation that we call N. So all the variables with N here is at the beginning of time step, so that means that I know the pressure and saturation in the initial of the reservoir simulation life, okay? And let's assume that this is a time step. Let's assume that this is a time step. When I'm solving this equation, that meaning that I'm trying to, let's assume that I'm using 30 days here as time steps. So what I'm solving this equation, that means that I want to know how is the pressure, saturation of water, and saturation of gas in what we call N+1 here. N+1 here is 30 days, okay? So when I do this equation here, that meaning that I know the pressure and saturations in time 0, and I want to find out which is the saturation pressure of time 0 that satisfies, that can put this equation here to 0, okay? So that meaning that when I'm doing this, I'm trying to solve the pressure and saturation here. So when I'm saying that I have a solution of, for example, in this case, I have a solution of 36 equations and 36 unknowns, okay? So I have to solve this. That meaning that I have to solve this to find the solutions in one time step. But if my reservoir life is 20 years, I have to do this many times, okay? I have to do this many times until the end of simulation run. I don't know if I answer your question, Ramin, but for example, if I cut the time step in 2 here, that means that I have to solve 36 equations to find this, and 36 equations again to find this. Okay, that's why we try to use the higher time step we can, because then we don't have to solve too many times. For example, if I go 20 years in the reservoir life, from 30 days to 30 days, I have to solve this 20 times 12 times, okay? If I go from 1 day to 1 day, then I have to solve this many times. That's why I try to use time step that's a little bit higher, so the simulation doesn't take too much time to run, okay? So I hope I answered your question, Romy. I'm going to talk a little bit about this time step selection here. This is not an issue today because the simulations, commercial simulations today, they calculate the time step automatically. But in the past, we used to have to select the time step. It was a very important thing to know, because if I use a time step too big here, I'm going to use, sometimes I don't have conversions, so I have to go back and solve everything again. So this takes times of the simulation. And also, if the time step is too big, the solution of the end of the time step is different from the solution of the beginning of time step. So most of the time, I use more iterations to get to 30 days. For example, if I use 30 days, I would take 5 iterations to run. If I have 15 days, I use do 2 iterations, for example. So it's better to do 2 iterations plus 2 iterations, which would be add 4, compared to 5. So it's not, there is an optimum size of time step, because if it's too small, I have to solve it too many times. If it's too big, then I have too many iterations to solve. So there is an optimum here. We're going to talk a little bit about this today. But we don't have to study this too hard, because the simulations today, they calculate this optimal time step automatically inside the simulation, okay? And why we consider the residual equal to 0? Why it's 0? Because it's here, okay? The residual equations are these equations here. So the residual equations, I'm adding the flux terms plus the accumulation terms plus the well terms. If I add all the mass that's going in and out and accumulating, it has to be 0. So this is what I'm calling residual. So it must go to 0 all the time, okay? Okay, so when I solve this, of course, my residuals are, if I have n blocks, I have n residuals, and each residual here has 3 terms: oil equation, water equation, and gas equation. And my unknowns are also a vector of n blocks, and each of these x here have pressure, saturation of water, and saturation of gas, okay? And once we have this, we have to solve this many times. We have seen this in last class. We finish in this point. So I have to guess, I have an initial guess of X, which is this pressure and saturation. I have to guess pressure and saturation of all the blocks. Once I have all the saturation, I calculate the residuals. If the residuals are 0, then I reach the solution. If they are not 0, I have to calculate the derivatives. Once I calculate the derivatives, I'll calculate the next pressure and saturations of the next iteration. Once I calculate the next pressure iterations, I check if I have conversions. If I have conversions, then I will go to the next time step. If I don't have conversions, I have to go back here and solve for another iterations until I reach conversions. The same way we have seen these equations here. So this is, for example, what we call XU. One iteration, then I calculate the derivative, then X plus 1. Here's J instead of U. Okay? It's wrong here. It's the same thing as here. Okay, a little bit wrong here. So iteration J here is going, and then we calculate until we reach the residuals. So instead of one equations, we have to solve for many equations. Okay.
Excuse me, Professor.
Yes.
I have one question. In the last class, you told us that for convergence, we should consider both residues and x values to be in a tolerance. Could you please give some explanation why we should consider also x?
I'm explaining it. Let's assume that this function here is like this, okay? And let's assume that this is my tolerance. What we call here the tolerance of residual is E2, for example. So what means that this tolerance? So if the residual is inside E2, then my solution is reached, okay? So my residual is small. Why we also use this one? For example, let's assume that I'm trying to solve here. I give my initial x 0. Then I calculate the derivative. And then I calculate a new one here. And this is inside the tolerance, okay? Let's assume that this is my solution. So I give this initial guess, I calculate the derivatives, I go here, and this is inside the tolerance. As you can see, this is inside the tolerance, but it's very far from the 0 here. So there are some equations in the simulator that has this behavior. They converge very slowly to the solution. So if they converge very slowly to the solution, sometimes I'm inside the residual for the tolerance for the residual, but I'm still very far from the solution. So the simulation also includes this second term here, meaning that if x0 is very different from xy, then even if I'm inside the residual of tolerance, I'm going to give another iteration and calculate again. For example, I have x2 here, and this is still very far from x2 first inside. So I calculate again, and then I have x3 here, and then x4 until not only I'm inside the residual here, but the x is changing, is not changing too much. So that's meaning that if this type of equation happens, I assign sometimes the tolerance for residuals, but the variables, the pressure and saturation, are still varying too much from one iteration to another. So the simulation keeps doing more iterations and more iterations until we have a better solution. Okay. I don't know if it was clear.
Yes, thank you.
Okay. So that's why most of the simulations have these two convergence criterion, not all the simulations. And again, there are a lot of things that I'm talking here that the user have to choose this in the reservoir simulation keywords as usual. The user will, for example, if I want to have a very fast convergence rate, I can take out this. For example, if I have a lot of uncertainties in the reservoir, if I'm interested just in an initial solution and I don't have a very robust solution, and I can take out of this equation here from the tolerance, and then I'm gonna get a solution only if the second one is gonna converge much faster, but the solution will not be very good. So the residual will not be very good, but the solution is faster. So again, there are a lot of things that we have to select in the reservoir simulation keywords that will affect the speed of the convergence. So the simulation will go faster, but also will affect the quality of the solution. So if I want a very good quality solution, then I'm gonna have to wait more time. I'm gonna use a smaller residual, I'm gonna use these two, I'm gonna use more grid blocks, a smaller time steps, and this one, the solution will be better, but sometimes instead of running in half an hour, it's gonna run in 3 hours. So I have to select according to my objectives, what's the type of solution I want, okay? There was a microphone, some questions. I don't know if someone would ask something. Okay. Okay, this is a review of the last classes, and then we are gonna go to the new subject now, which is part 4. And for here. Okay. Do you have any questions about the solutions, anything? So sorry, this here is a little bit long. 15. Okay. Just a second. This is also in Portuguese. Just a second. I'm gonna take the version, English version. I took all the Portuguese version today. Sorry. Just a minute. And I also would like to thank Danielle that translates everything for me. Let's take here part 4. Part 4. Okay. Okay, this is the correct one. Okay, today we're gonna talk a little bit more about the solution, about the time steps, and about the well behavior. Okay, so today we are gonna try to finish the black oil model, because next class is a test already, and then the project's presentations. So I'm gonna try to finish the black oil model, which is the basic model we can have. Okay, so considering the grids, we have talked about these last classes, but just put again here, we have Cartesian grids, cylindrical grids, local refinement, corner point, and Voronoi. So the most used grids we have today are the Cartesian, because they are easy to build, and they converge much faster than the others. And the corner point, especially for the complex geometries that we have in the carbonates, for example, and so on. So the corner point can adapt better for the complex geometries we have. And we also sometimes use the local refinement, especially close to places where we have we want a better solution, a finer solution, especially around wells, for example, okay? So these are the three main grids we use today: the Cartesian, the corner point, and together with the Cartesian and corner point, sometimes the local refinement, okay? And again, if I'm going to use, for example, local refinement here, I'm adding new blocks, and adding these new blocks, I'm adding new equations, and the solutions will be is lower, okay? So if I add more blocks, of course, if I have more blocks, the solution will take more time to run. Also, if I add more blocks that are very small as this one, we're going to see today that for a small block like this one, we have a time step that is proportional of the size of the block. For example, if I'm solving for this size of the blocks here, I can use a time step that, for example, 30 days. But for this one, as the block is too small and pressure and saturations are changing too much, sometimes I have to use a smaller time step, for example, here, 5 days. So once I add these complex geometries and smaller blocks and local refinements and so on, the solutions is not only take more time because of the number of the blocks, but also because of the characteristics of the block. When we have very small blocks, the time steps also will have to be small. I'm going to show this today in the equations, but this is a very important thing for you to consider. So you can try to, now that you can use the simulations, for example, the IMAX, you can try to put here, for example, if you put local refinement in all the wells, sometimes instead of 1 hour, you run your simulation in 2 hours, for example. So you have to be very careful when you use these local refinements and these complex geometries, because the simulation time will increase a lot, okay? Another hint about grid orientations. It's very important for you to try to have a grid orientation that is according to the permeability orientations. For example, why this is happening? Because if the fluid will have a tendency to move in the direction of the higher permeability we have. For example, if we have a higher permeability in this X direction here, the fluid will have a tendency to move easier in this direction. So it's very a wise solution to orient our grid in this direction. Sometimes it's not easy to do it because we have a grid that's complex, a geometry that's very complex. But if you can use this, it's also a good solution. Okay. Another thing that's very important is try to follow the geological trends we have in special geological layers and facies, for example. That's happening for the same reason. For example, if I have several facies in the reservoir and some facies have higher permeability than the others, then I have to try to orient the grid in this or the same orientation of these facies. Okay. The grid refinement, of course, we want to use is a function of the physical model, and we want to use a higher refinement where we are trying to have a better solution. And this, of course, is when we have a higher or abrupt change of flow conditions, close to wells, in very heterogeneous regions, for example, because if it's very heterogeneous, I cannot an average of the permeability, the upscaling is not very good. So it's very wise choice to use a more fine grid blocks. And also to map better flow conditions. Of course, we're gonna, assuming that when I have these refinements, I'm gonna decrease the time step and increase the simulation time. I have to be very careful to include this local refinement. So the most of the time we use local refinement only in the wells, okay? But if you have any other of these other conditions here, you also can use local refinement, okay? Also, it's not recommended to use wells in neighbor blocks. For example, if you have an injector here, and a producer here, we are going to show in the equations that it's not very good to have an injector neighbor of a producer. So if we have a condition like this, we normally do a refinement. So we can have, for example, this thing here and this thing here. For example, instead of running this thing, I can refine this grid and this grid. So I have these blocks. I have a better fluid calculation, fluid movement calculation from the injector to the producer when I have a refinement like this, okay? And also, from several studies that are in the literature, they do not recommend to have very abrupt changes from one to another. For example, what is this relationship 1.5? For example, here, I'm gonna have a relationship from one coarse block to 3 fine blocks, for example. So I have a relation 3 to 1, okay? So if I have a very refinement here, for example, 10 blocks here, too much, I would have a relationship 10 to 1. This is not very good to have because we have higher numerical errors when we have these conditions like this, okay? So sometimes when it's not good to refine too much because we are increasing the quality of the solution inside the block, but we have a worse quality when we are calculating the flux from the refined part to the coarse part. So a good alternative is use at most 1 to 3 or 1 to 2, okay? And of course, higher grid refinement, higher cost, okay? The ideal thing is to do a sensitivity analysis, of course. If, for example, if you simulate this condition here, and then you simulate this condition here, and the quality of the solution is almost the same, and this is half of the time, of course, I'm gonna use this solution here, okay? So what we're calling sensitivity analysis, we can do before we do thousands of simulations to history matching or to optimize solution, this thing. We normally do sensitivity analysis in all these things here to see if the solutions change too much. So trying to find a solution that is faster and with the same quality, okay? So there are a lot of things that are in the literature about grid orientation, about grid refinement, and so on. If you are more interested in this, it's very important for you to read all this material in the books, Matax and Nazis and the other books that we recommended. Also, there are a lot of hints in how to select grid orientation and grid refinement, okay? Remember that the matrix that we are going to solve is a function of our grids. And so if, for example, here, if I have a 1D grid, we're going to have, for each block, we have 2 neighbors. So we're going to solve for a matrix that's like this, okay, of course. If I put a refinement here, then we are adding blocks, we are adding other points here. For example, here I would have block 10 and 11, 12, 13, 14, and so on. So the one will be a neighbor of block 10, block 13, and so on. So once we have a refinement here, we're going to have a matrix that's more difficult to solve. This matrix is very easy to solve for those who are familiar with the solution, this type of solution. Notice that tridiagonal matrix like this one is easier to solve than a matrix that's a sparse matrix here, okay? But remember that this matrix that we are gonna solve is a function of the grid. That's why we have to select very carefully the grid, because the matrix will take more time or less time to solve according to the choice of grid we are solving. And here we are solving some examples for 1D. Here is an example of a 4D, which is pentadiagonal, because we have, in each line here, we have 5 terms, okay? Because each block here has 5 neighbors, or 4 neighbors plus the neighbor we are calculating. If you have a 3D, we have a diagonal because each one have 6 neighbors plus the block. For example, this one has 6 neighbors plus the block. Okay, so it's a little bit harder to solve 3D. And of course, if I have a more complex grid, I'm going to have a more complex matrix. Okay, and this is one of the reasons I told you last class that the Cartesian grid is sometimes people say that Cartesian grid is not good because it's not aligned with the geology and so on, but that the Cartesian blocks are much easier to solve because of 2 things. One thing that's the Cartesian grid will have a very well-behaved matrix, so it's easier to solve. Once I know that I have a heptadiagonal matrix, I can use a solver that knows this and don't have to calculate all the other terms here and so on. When I have a complex grid, I have to solve in another way, which is more complex and takes more time. Okay, so a Cartesian grid is easier. Another reason for having a Cartesian grid that we're going to see now, the hints for discretization in time, is that for bigger blocks, we can have higher, bigger time steps as well. So when I have a Cartesian grid, I can run a time step that's higher than for example, when I have grid refinement. Okay. So this is what I had to say about grids. And here I'm going to talk about a little bit about discretization in time. Remember that we have seen this again. The time step will take us from the beginning of the time step until the end of time step. So I know the pressure and saturations in the beginning of the time step, and solving the matrix, I'm going to find the solution for the next time step, so n+1. So for example, if I'm running from 30 to 30 days, I know the solution in time 0 because I know that the reservoir is in initial conditions which are given. Solving this matrix, I'm going to find the solution for time 30 days. Once I find the solution, I'm going to go to 60 days. And once I find the solution, I go again to 90 days and so on. Okay, so that's why. So the simulation will go until the end of the simulation time, the end of the reservoir life, or until the time you are interested in simulation. Okay. But there are some considerations, important considerations about the discretization in time. The time step control is important, especially for implicit methods, because the higher is the time step, the higher is the truncation error. Do you remember that when we did the discretization of the variables in time, we used this simplification here. The variation in time of the variable is the variation divided by the time step. But we have an error that is in the order of the size of the time step. So if the time step is smaller, then the solution is a little bit better, or the truncation error is a little bit smaller, okay? So, for example, if I run the simulation from 30 to 30 days, I have a quality of the solution. If I run the simulation from 15 to 15 days, the solution is a little bit better because this truncation error is smaller, okay? If I run the simulation from 1 day to 1 day, 1 day, 1 day until the end of simulation, the solution will be, of course, better than if I have a 30 days of 20 days. But of course, I'm going to take almost 30 times more because I have if I go from 1 day to 1 day, I have to solve 30 times here until I get the solution for 30 days. And here I have to run just one time step. Okay? So this is much faster than this one. Of course, this relationship is not like this because from 1 day to 1 day, probably I'm going to converge in 2 and 1 iteration. So I'm going to take here, I don't know, 40 times. And here, I'm going to take, I don't know, 5 iterations. So I'm going to have to compare this with this, okay? But of course, if I run from 30 to 30 days, it will be a little bit faster, but the error will be higher, okay? And also, if the time step is higher, the number of iterations, as I'm telling, is higher because the solution changes a lot from 0 to 30 days. So I'm going to take more iterations. So at the end, the total time of simulation time is not the number of time steps, but the number of time steps time the number of iterations per time step. So that's what I was telling here. So if, for example, I'm running for 1 year total, and the time step is 30 days, and the average conversions in time step is 5, as I'm telling here, I'm gonna take 12 time steps times 5 iterations, which will be, I'm gonna solve 60 times, okay? If I run, for example, the time step let's assume here 6 months, let's assume a very radical solution. I'm gonna take 2 time steps, but I'm gonna converge in 10 iterations, for example. Then I'm gonna solve here in 20 time steps. So it's faster to do in this way, okay? Of course, the error will be higher here. The truncation error is higher if my time step is 6 months than 30 days. And of course, if I use 15 days, the time step is a little bit faster and the truncation error is smaller and so on. So I have to consider these 2 aspects, the simulation time, which is this, the number of time steps times the number of iterations, and the quality of the solutions. That, of course, I want, of course, a smaller truncation error. So I want to use the smallest time step I can if the simulation is faster, okay? So in the past, we used to do a control manually of this time step. And today, this control is automatic by the simulator. And I'm going to explain how the simulation works, okay? So the time step control is basic done. I'm going to explain this option here, which is the most common in the simulator, is based on the variation of the primary variables, which is saturation and pressure, okay? And how it works, here's an example, for example. Let's assume that I have a time step that's delta t here. And the user will say that I have a maximum change that I can accept from the beginning to the end of time step of my primary values. Let's assume, for example, that I don't want to change more than 50 psi in pressure, and I don't want to change more than 0.05 of the saturations, okay? So what the simulation does, it starts with a very small time step, for example, 1 day, and then it do the conversions of 1 time step, okay? And then it calculates the variation in pressure and variation in saturation from the beginning to the end of the time steps. And these are the maximum I can accept, okay? So let's assume that I have these values here, 50 for pressure and 0.05 for saturations. And let's assume, and this first, I changed 3 psi, 5 psi in 1 day, and I changed 0.001 in saturations. So I compare these values with the maximum values the user accepts. So as these values are smaller than these ones, then it's going to increase the next time steps. Let's assume we are doing now for 2 days. Let's assume that now for 2 days, I have 20 psi of variation in pressure and 0.01 of saturation. These are still smaller than this one. So let's assume I'm going to go now for 4 days. And let's assume now for 4 days, I have 60 psi of pressure and 0.02 of saturation. This one is okay because it's smaller than this one, but 60 is higher than 50. That's the maximum pressure the user accepts. So then I can, in the next time step, I will decrease this to 3 days. because the saturation, the pressure is changing too much, so the simulation try to decrease the pressure. And then it do exactly like this. So it increases the next time steps. Is the variation pressure saturations are below our maximum that we accept, and decreases and increase the time step according to these changes. So we don't have, the user don't have to bother anymore with these changes. The simulation does this automatically. Okay. And of course, there are different ways to manage this. For example, if the maximum is above the maximum, I can decrease the time step, or I can cut the time step and solve again. Of course, if I cut this time step and solve everything again, that's gonna take more time to run. So what the simulation normally does is use, for example, a term here. The next time step is proportional to the last time step and proportional to the change. For example, in this case here, let's assume I'm here, for example. It's 20 is, let's put 25 here. 25 is half of the maximum. If 25 is the maximum, half of the maximum, I would double the time step. But instead of double, it multiplies a factor of 0.8, for example, because if I double the time step, then it's going to be very close to the maximum value, so it doesn't change too much. There are several ways to do it, but the most important thing here is not the way the simulation does, but the user. This is automatic by the simulation, and they use a formula that is proportional to these changes. The most important thing for you is that you have to inform these values to the simulator, the maximum pressure and maximum saturations that you accept. And this, of course, will change according to the case you are running and according to the precision you want for your solution. If you want, for example, a faster solution, you can use a higher value here for pressure and saturation, because the time step will be higher. Okay. If you want a more precise solution, you use a more smaller values for pressure and saturation, maximum saturation, so the time step will be smaller. Okay. So you don't have to care too much about this control, but you have to inform this to the simulator. And now, again, be aware that the simulation have a lot of defaults, right? What means defaults? If you don't inform anything, the simulation will take a default value for this. That you have to look into the manual and see what's the default for these values. And normally the default is something that makes the simulation run faster. Okay. So be careful about this. Okay. Another way to control the time steps, let's assume that you use the default, and the default of simulation is 500. Okay. Another way to control these things is at the end of simulation. I don't know if you have seen this in your projects with your tutors, but at the end of simulation, there is a calculation of the material balance of the equations. Do you know what is this? Anybody talk about this for you in the last classes? No answer. You know, Daniel, if anyone talk about the material balance for them?
I think João, maybe João.
João talk. Okay, so one way to control this, if João, I'm not gonna repeat it, but the material balance, basically, do you remember that we had the residuals, which are the flux terms plus the accumulation terms plus the well terms, and this have to go to 0. And we have a tolerance to solve, right? If you have an equation that's like this, we are solving for a tolerance. We are gonna converge, and this is the answer. So my residual is not exactly 0. It's something that's small and close to 0, but not exactly 0. So what the simulation does, it calculates the material balance, calculates the absolute value of the residual, and then it calculates all the residual for all the time steps and adds all this. That means that at the end of the simulation time, if the residuals are accumulating too much and the material balance is too big, then you can look in your simulation files, in the output files, and see that your material balance is too high. So then you can decrease these values, for example, or decrease the maximum time step size and so on. And then you're gonna see that the material balance will decrease. If the material balance decreases, that means that you have a better solution. So if you want an even better solution, you have to decrease again the time step or decrease the size of the grid and so on, okay? So one way to control your errors and to check the solution is good or not is to look into the material balance at the end of your simulation runs, okay? But of course, the way that simulation controls is using this automatic time step control here, okay? Okay, I'm gonna remember, I'm gonna talk just faster about the implicit method here. Remember that we have an implicit method as well. I'm gonna talk a little bit of this to explain you how the IEM, which is the adaptative implicit method, which I told you last class that it was a good solution. Most of the things in the simulations are, can simulations optimize the iteration number? No, I mean, the iteration number is a function of their tolerances, okay? So it will calculate iteration 1, 2, 3, or 4 until reach a tolerance. So we cannot optimize the iteration number. We normally try to optimize the size, this simulation time here. So the simulation try to get the best relationship between the number of iterations and time steps, but not the iterations, okay? What normally we want is the best simulation time. So the best simulation time will be a function of the average iterations and the number of time steps. So we cannot optimize the iteration numbers, but the iteration number is a function of your residuals, okay? A function of your tolerances. Did I answer your question? Okay. Okay, so if I have an implicit solution, again, we are solving for, remember that each of these terms here are a matrix that have to solve for pressure and saturations, okay? And the equations, sorry, here, pressures and saturations. And the equations here are equations of oil, equation of water, and equation of gas, okay? However, if we want a faster solution, we can try to use the implicit formulation. What is implicit formulation? It's implicit for pressure and explicit for saturation. What means that? Remember that when we call n, it's the beginning of time step, and when we call n+1, it's the end of time step, and we are trying to solve from n to n+1. Okay, so when I go to n+1, I know all the variables in n, and I want to calculate the variables in n+1. So when I have all the residual equations, I can treat the pressure and saturations at the same time that we call an implicit method. So we solve for pressure and saturation at the same time. So pressure and saturations will be the index n+1, okay? But if you use an implicit method, we're gonna treat the pressure implicitly and treat the saturation explicitly. What that means that all the terms that depend on saturation in the equations will be treated as knowns, not unknowns, okay? Of course, if I do this, instead of solving 3 equations and 3 unknowns, I'm gonna solve 1 equation and 1 unknown, and 1 unknown is pressure, and 1 equation will be a combination of the 3 equations we have. I'm gonna check very, very briefly how we do it here. And of course, if instead of having, for example, for 1 million block, instead of having 3 million equations, I'm gonna have 1 million equations. So it's gonna be much faster to solve this equation. So if it's Then when I calculate the pressure, then I go again into the equations and then I solve for saturation. So I solve first for pressure and then I solve for saturations. I'm going to explain a little bit, then I go back. I'm going to explain the implicit, we solve everything at the same time. The implicit, I'm going to explain here. And the IM, I'm going to explain how the CMG did it, invented this method, and all the other simulations, they have a similar method because it's a very good idea. Okay? So I'm going to explain very briefly the implicit method here. The implicit method here, again, is implicit for pressure and explicit for saturation. So let's assume I have a two-phase simulator that we have only pressure and water saturation as our equations. So if I have implicit method, both will be treated n+1, okay? If I use an implicit method, then the pressure will be n+1 and the saturation will be n. So will be treated as n. So for example, here I have the residual equations. I'm not gonna explain how we did it, but we combine the two equations here into one. So we have one equation only, which is a combination of the water residual calculation and oil residual calculation. I'm going to combine in two. What's the objective of this combination? To eliminate the water saturation as unknown here. So I'm going to, in this example here, multiply by these functions here, add the two equations. So I'm going to eliminate water saturation from the equation, and I'm going to keep only the oil, the pressure as our unknowns here. So instead of having two equations and two unknowns, I'm going to have just one equation and one unknown. Okay. Once I do this, I solve for pressure. And once I have pressure, I go back to the equation and solve for the water saturation. So I'm going to solve these equations in two steps. First, I solve for pressure, and then I calculate the saturations. Of course, this would be a good idea, except for by the fact that some of these terms here, this here I simplify here to show the combinations. But remember that these terms here, the transmissibility here, they are a function of relative permeability, for example. And the relative permeability is a function of saturations. So I have to treat, for example, relative permeability as unknown, as the constant in the beginning of the time step. So the quality of the solutions will be not so good as the quality of the solution for the implicit. So again, I'm changing a little bit I have to select the best relationship between simulation time and quality of the solution. So if I use a simulation implicit, I expect better solutions. And if I use a simulation implicit, I expect faster solutions. And I have to select the best one. Just to give you an idea and how faster and how, for example, in an implicit solution, the amount of calculations we have to do is proportional to this variable here, C, I, J. Ij are the dimensions of the grid. If I go to the implicit solution, it's 27 times more calculations to do in the implicit than the implicit. So that's why the implicit normally is faster. And I have a memory that have to be 9 times higher than the one, okay? However, there is a major problem with the implicit method, that the time steps, because we are going from the beginning to the end of the time step. Remember that we are treating all the function of saturation explicitly. So the relative permeability, for example, is treated explicitly. So in the implicit method, I cannot use too big time step, because if I have a too big time step, it will not converge. Why? Because the solution is not good. For example, if I have 30 days, the relative permeability will change a lot from the beginning to the end of the time step. So it's not a good idea to use a time step too big and using an explicit solution, using variables that don't change in the time step. So normally, when we have implicit solution, we have smaller time steps. So again, we have to be careful, because the we have to solve just one equation instead of 3. So the solution is 20 times faster, 27 times faster. But if my time step is, I don't know, 20 times smaller, then I have to check which is the best solution here to do, okay? So again, when people say the implicit solutions is faster, you have to be careful and not always. Normally, the implicit solutions is faster, but because the time step sometimes is very small, the solution will have to perform too many time steps. Sometimes the implicit solutions is even takes more time than implicit methods, okay? So be careful about that, be careful. So we have this comparison. The implicit methods has less unknowns to solve. And I'm gonna not show here, but if you are more interested, there are some literature showing that the numerical dispersion is a little bit smaller than in the implicit solution, okay? But there are some disadvantages. It's not stable because of this. The time step has to be small. If it's too big, it will not converge. So if it's not converged, I have to cut the time step and solve again. So instead of running an implicit solution, I'm running implicit solution, and there are a lot of convergence problems. Then I have to check the solution to see if it's really faster, okay? And the time step has to be smaller. So you have to be careful about these two terms here when you are using an implicit solution. So of course, the selection of the formulation will depend on the physical problem and the grids, okay? So the CMG, that's the builder of IMAX and GEM and so on, have this solution that they invented this solution. Today, almost all commercial simulations have, which is a method that's adaptive implicit method. I'm going to explain very briefly here because the introductory is here. But let's assume I have a very simple problem here that I'm injecting water here and producing fluids here. Okay, here's a producer and here's a water injector. Let's assume I have oil here and water, and I'm displacing oil here, injector. And I have a grid size, which is this one, for example. Okay, what this method, this adaptive implicit method does, it does like this. I know that water, for example, in the beginning of the time step, the first time step, for example, the water saturation is changing a lot in this block. But after some time, the water is displacing oil. All these blocks here are filled with water. In this part here, we have water displacing oil. And in this part of the reservoir, we have only oil moving, and we don't have still water moving here. So if I use an implicit method, I'm solving for water, oil, and gas, if you have gas as well, or arterial. Let's assume it's a two-phase. I have to solve for water and oil in all the blocks. So I have two equations per block. This method, IM block, it calculates the variation in saturation in the last time step. For example, in this block, as we don't have oil moving, but only water moving, it will solve implicit. Let's assume these are the grid blocks, okay? So in the first block, as I don't have variation in the water saturation, it doesn't matter if I am solving pressure implicitly and water saturation explicitly, because the saturation is not changing too much. So for this condition, the simulation will use an implicit method. At the other extreme of the reservoir, for example, here, I have only oil moving. So I don't have water saturation changing here. So I'm going to use, again, an implicit method. So again, implicit method here, implicit method here, implicit method here. But in the middle of the reservoir, or in the region where the water is displacing oil, we are going to have pressure changes and also saturation changes. So in this region here, we are going to use implicit methods. So The simulation calculates automatically based on the changes in the last time step where the saturation is changing too much and where the saturation is not changing too much, and uses implicit and implicit formulation in the implicit formulation where we don't have saturation changes, and implicit method where we have saturation changes. So instead of solving, in this case, let's assume you have 1, 2, 3, 4, 5. Let's assume we have 6 blocks here, and we are, instead of solving 12 equations, we are solving 1, 2, 3, 4, 5, 6, 7. We are solving 7 equations. Okay. Of course, this is a very simple grid block. It's not too much, but assuming that we have 1,000,000 blocks, and in these 1,000,000 blocks, we have a lot of places that we don't have water saturation changes. Instead of using implicit, I'm using implicit. I'm gonna solve much faster, and the IM is much faster than the both. And it has the advantage of both because it's faster and also a good solution and a stable solution. So this is a choice that if you can use in our simulation is always a good choice. Okay. For example, I think here in this example here we have a 9-block, a 2D example with 9 blocks in the well completion in blocks 4 and 5, for example. So we have water changes here, pressure changes here. So at the end, we are gonna, instead of having this solution, which is the implicit method, and we are solving 3 equations per block plus the equation of the well, I'm gonna solve the implicit IM method, which is this one, which is much faster. Okay. Of course, this is very brief. It's not a very deep subject, but if you want to understand more about how is the implicit method and how is the adaptive method, implicit method works, there are a lot of information in the books and also in a lot of papers. But basically is this, today in the commercial simulations, if you can use adaptive implicit method, is a good selection because you don't have the same thing as time step control. In the past, it was very hard to select the best time step for the simulation, but today we don't have to care too much. We just care informing these things here, and the simulation calculates automatically the time steps. So for the formulation, it's the same thing. We don't have to care too much. You have to just inform that we are using the adaptive implicit method. And the simulator will automatically calculate implicitly where it's necessary and implicit where it's not necessary. Okay. So this is the basic thing. I'm not gonna read these things here, but here in the Matrix book, which you have in the literature, you have in the library as well, I select a few hints about these formulations here. And of course, this will be available in the material that Daniel will put for you. You can read this, or you can read in the Matrix book, okay? So you can understand a little bit more about that. Do you have any questions about this, about the time steps, about the implicit and implicit and IM formulation? Okay, if you don't have, maybe it's a good time to do a break. We're gonna do a 10-minute break from 9:30 to 9:40. So we're gonna come back in 9:40, and we're gonna explain you the well treatment. Of course, João give you a little bit of that, how we integrate this reservoir simulation with production facilities. And now I'm gonna give you more hints about how we're gonna treat the well in the simulators, okay? So see you in 10 minutes here. I'm gonna stop recording and start again after the interval.